Particle Physics and the Standard Model by Rahul Deshpande. Ever wonder what the world is made up of? Everyone knows that the world is made up of matter, which is in turn made up of particles. But what are these particles? Well, the answer lies in particle physics. Particle physics is the science of really, really small things. See, there's a particle. Particles include quarks, leptons, and bosons. Well, now you ask, what are quarks, leptons, and bosons? Quarks make up protons and neutrons. There are two parts of an atom, in case you didn't know already. Leptons, on the other hand, make up electrons. Those little swirly things you see around sciencey drawings of atoms. The third main kind of particle is the boson. Bosons carry force. There are four different forces: electromagnetic, gravitational, weak, and strong. It's kind of counterintuitive because gravitational force is the weakest, while weak is the second weakest. Strong is the strongest, no duh, and electromagnetic is third strongest. Particle physics depends on this thing called the Standard Model. The Standard Model is pretty much the periodic table, but for particles. Here's the gist of the Standard Model, which was developed in the early 1970s. Our entire universe is made up of 12 different matter particles and 4 forces. Among those 12 particles, you'll encounter 6 quarks and 6 leptons. Quarks make up protons and neutrons, while members of the lepton family include the electron and electron neutrino, its neutrally charged counterpart. Quarks make up protons, and leptons make up electrons. Quarks also make up neutrons, as previously covered. Scientists think that leptons and quarks are indivisible. You can't break them apart into smaller particles. Along with those particles, the Standard Model also acknowledges 4 forces: gravitational, electromagnetic, strong, and weak. Let's focus a bit on the quarks. They're also arranged in 3 generations: up, down, charm, strange, and top, bottom. The bottom quark can also be known as the beauty quark. Cool, huh? The 6 leptons are arranged in 3 generations: the electron neutrino, the muon, and the muon neutrino, and the tau neutrino. The electron, the muon, and the tau all have an electric charge and a sizable mass, whereas the neutrinos are electrically neutral and have very little mass. Phew, that was a lot of facts. Your brain is probably bursting with them by now. But don't worry, this isn't the end. We're going to learn lots and lots more in this video. There are 4 different bosons, but only three forces are acknowledged in the Standard Model. The photon, represented by by this symbol, transmits the electromagnetic force. The gluon, here, transmits the strong force. The W and Z bosons, as represented here, transmit the weak force. But then you might be thinking, where's gravity? Gravity is a force too, right? You're right, it is, but its boson hasn't been discovered yet, and so it's not part of the Standard Model. But what about the Higgs boson? I heard about that. Isn't that real? I heard that they found one about 3 years ago. Well, yes, they kind of did find one, but they haven't proven that it is the Higgs boson yet. The Higgs boson does fit in, but we'll talk about that now. The Standard Model is a theory. The theory describes the subatomic particles that are the basic building blocks of the universe, along with how they interact. But theorist has a problem. Their equations only worked if particles had no mass. That was an impossibility in a universe located with stuff such as stars, planets, and people. If they imagined that the particles were all massless, then each term in the equations clicked into a perfectly symmetric pattern, like the tips of a perfect snowflake. And this symmetry was not just only mathematically elegant, it explained patterns evident in the experimental data, but, and here's the puzzle, physicists knew that the particles did have mass, and when they modified the equations to account for this fact, the mathematical harmony was spoiled. The equations became complex and unwieldy, and worse still, inconsistent. What to do? Here's the idea put forward by Peter Higgs, the person who discovered the Higgs boson. Don't shove the particles' masses down the throat of the beautiful equations. Instead, keep the equations pristine and symmetric, but consider them operating within a peculiar environment. Imagine that all of space is uniformly filled with an invisible substance, now called the Higgs field, that exerts a drag force on particles when they accelerate through it. Push on a fundamental particle in an effort to increase its speed, and, according to Higgs, you would feel this drag force as resistance. Justifiably, you would interpret the resistance as the particle's mass. For a mental toehold, think of a ping pong ball submerged in water. When you push on the ping pong ball, it will feel much more massive than it does outside of water. An interaction with the watery environment has the effect of endowing it with more mass. So with particles submerged the same with particles submerged in the Higgs field. In conclusion, particle physics studies small things, particles. It depends on the Standard Model. The Standard Model is a theory of subatomic particles. Hey kids, there's a vocab word. Subatomic means really, really small. Back. The Standard Model is a theory of subatomic particles and how they interact. The Higgs boson is a part of the Standard Model, and it gives mass to other particles. Don't forget to like, share, and subscribe so that all your other friends that haven't seen this video can learn some more great science. Bye.